So in the last video, we designed a simple decade counter. And this video will start with an up counter. And this again is a counter. So an up counter is a counter that counts from some lower number to some higher number in the increasing order. As the name suggests, it's an up counter. It starts counting upwards. Fine. In that sense, decade counter is also an up counter because it starts from 0 and count up to 10 before being reset back to 0. Right? So let's come up with a problem. So let's design an up counter that counts, let's say, from 0 to, let's say, 7. Fine. And then resets back to 0. And then resets back to 0. But I will add one more twist to this. We'll also assume, so let's assume that each state transition, that means the condition of moving from one state to another state, in the decade counter we had assumed that that condition is governed only by the clock. So every time a clock comes, there will be a transition from current state to next state. But here we will assume that each state transition, apart from the clock which is implied, it is also governed by an external input. Let's call that input B, in such a manner that only when B is equal to 1, then only you can transit from current state to the next state at the next rising edge of the clock. Fine. So going by the methodology, the first step is we have to capture the finite state machine. So this is the first step. We capture the finite state machine. Fine. So it's pretty straightforward. We start with the state 0, then state 1, state 2, 3, 4, 5, 6, 7. So we'll have 8 unique states. Fine. Then we have to choose an initial state. Let 0 be the initial state. Then the transitions. So if I have to move from 0 to 1, I have to make sure B is high. In case B is not high, so I will continue to stay in the same state. Then again from 1 to 2, I'll have to make sure B is high. If it is not high, then I will continue to stay in the same state. Likewise, from 2 to 3, I have to make sure B is high. If B is not high, I will continue to stay in the same state. 3 to 4, B should be high. Otherwise, I will stay in the same state. Same happens for all the states. 5 to 6, B should be high. Otherwise, I will stay in the same state. 6 to 7, and then back 7 to 0. So this will be the finite state machine for this problem. Next, we create the standard architecture. Wherein we resolve the sequential part, the memory part. So we'll have a combinational part, which is yet to be resolved. This is the combinational part. And we will have the sequential part. That is, we have resolver. What is the nature of my state register? Fine. Now I have 8 unique states. starting from 0 to 7. Fine. And if I assign a unique code to each such state, so 3 bits are sufficient. Fine. So in this case, I will have to use a 3-bit state register. Fine. And the outputs from this state register will go something like this. Let this be S2. These are the state outputs: S1, S0, S2, S1, S0. And then I will also have the next states. So N0, N1, and N2. Fine. Put an arrow here. So this one is N0. Yeah, we can write it here only in the combinational part. N0, N1, N2. This is the combinational logic. And additionally, we will have an external input. This right here. So this is my input B. Fine. So this is the standard architecture for this kind of an up counter. We have resolved with this memory part. That is, in the sense, we will be needing 3-bit state register. Then third step is we have to encode the states. So third step is encode the states. Again, in this case, it is pretty straightforward. I mean, for every state, you will use its binary equivalent. So encoded states will be something like this: 0, then for 1, 2, 3, 4, 5, 6, and say 7. So then encode them like this: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Fine. The transitions will still stay the same. So this is for B. Then B complement will stay in the same state. And as usual, we'll have some initial state, which we have chosen this state. Now from this encoded states, we have to create a state table. Fine, so let me just push it to this side. This is the encoded FSM. So we have to create a state table. Again, same process. On one side, we will list the, so this will be the fourth step: create the state table. And the state table is created wherein we list inputs on one side, both state inputs, and if you have external input, those also, and the outputs on the other side. Now in this design problem, in this example, we have both types of inputs: the external input and the state input. So create a state table listing both the inputs. So let's draw a line here. One, we'll have 16 different combinations. So I'll first draw the table. So we'll have state inputs S2, S1, S0, and then the external input B. Then accordingly on the output side, we don't have an external input on the output side, we just have the three next states. Fine. So let's fill the table. So we have S2, S1, S0, and external input B. And then we have N2, N1, N0. So 0, 1, 0, 1, 5, 6. Okay. Then we work our way combination by combination. So if my current state is 0, 0, 0, and B has a value of 0, my next state will still be 0, 0, 0. Fine. On the other hand, if my current state is 0, 0, 0, and B has a value 1, then only I will move to the next state 0, 0, 1. Fine. Likewise, if my current state is 0, 0, 1, and B is 0, I will continue to stay in the same state. But if B is 1, then I will move to the next state 0, 1, 0. Likewise, we will complete the table. For B is equal to 0, we will be in the same state. For B is equal to 1, we will be moving to the next state. And you will see these will be the values. And for the final state, we will again reset back to 0, 0, 0. Fine. Now from there, we can get the Boolean expressions for your outputs N2, N1, and N0. Fine. So N2, there are no don't care conditions here because we have found the output for all the 16 unique combinations. For N2, it will be summation, you see 0, 1, 2, 3, 4, 5, 6, or 7, 8, 9, 10, 11, 12, 13, 14. So 7, 8, 9, 10, 11, 12, 13, 14. Similarly, for N1, it will be 3, 4, 5, 6, 11, 12, 13, 14. And N0, it would be 1, 2, 5, 6, 9, 10, 13, 14 from the table itself. Then as usual, we'll try to simplify it using the conventional methods. Like I have already simplified them here using the K maps, and these are my simplified expressions. Fine. Then to complete the counter, we will implement these equations. Fine. So let me just try to fit it in here. We already have a 3-bit state register. So say here is my, okay, sorry. So here is my 3-bit state register. Fine. Just push it upwards. So this is the 3-bit state register. And from this register, I have my 3 state outputs. S2, S1, and S0. So this is S2, S1, S0. And then I also have my external input B that will also draw. So This is my external input B. Fine. And using these four inputs, we will actually implement these equations starting with N2. So N2 is slightly complicated. I need S2, S1 complement. So I'll tap out a connection from here, another one from here, then use a NOR gate, combine these two using an AND gate. Then I have another term S2, S0 complement. Again, S2, S0 complement. Then S2B complement. So S2 from here, B complement from here. Then S2 complement, okay, S2 complement, S1, S0, S1, S0, and also B. Then all four I'll be combining using a single 4-input OR gate. Fine. So this will be my N2. And this actually I will feed like this to the state register. Fine. Then for N1, for N1 I have S1, S0 complement. So S1 is this, S0 complement. Then S1 B complement. S1 is this, B complement we can get from here. And S1 complement, S1 complement is this, S0, S0, B. We'll combine them using a 3-input OR gate like this. So this will give me my N1. Again, I will feed it back. I will feed it back like this. Fine. Then for N0, we have S0 complement B plus S0 B complement. So yeah, we can actually resolve it into S0 XOR B. So it will be S0 from here, B from here, then combine them using an XOR gate. That will be my N0. And again, we'll feed it back just like this. Fine. And this will be the circuit implementation of my up counter.